Okay, so I hope we have all already downloaded the software, and the QueensOD is actually a very small software, and it's just considered as a simple tool for you to conduct the OD estimation, especially if you have a very complicated network and you don't want to compute everything by yourself. Then QueensOD is a very convenient tool. So for the implementation of, well, in order for you to learn QueensOD, I also shared with you about several materials. There will be 3 files. I shared with you the first one, the QueensOD R 2.0, 2.1. It's the user guide, which will give you as the manual for you to go through all the functions about the software, and give you the very detailed explanation about what's this method, what's the series under this software, and also give you the explanations about what's the input files you have to set, and what's the format of those input files, and what's the expected output files, and how you can read the output file and collect the data for you to conduct the simulations or the transporting planning. So I will pick up the most critical information from this manual and show them in the examples for you to learn the software. And also there are two reference, which would be two paper published like 30 years ago to introduce the series applied for the development of this software. And I also included some of them in the notes. And if you want to know more details about the series, you can go to read these two references. Okay, so that's the materials that you might need for the for this tutorial. And regarding to the learning of the QueensOD, first of all, QueensOD is a very lightweight software, which will be especially applied for you to conduct the OD estimation with the real-world field flow observations. This is actually a different way from the 4-step model to do the OD estimation. From the 4-step model, we are trying to rely on the microeconomic theory. We are trying to conduct a survey about the populations, the employment opportunities, the income levels, and the car ownerships, and so on. Use this information and try to identify the also do some survey about the trips that those people is conducting every day, and build a relationship between the this kind of socioeconomic parameters and employment parameters with respect to the trip rate. And we can either use the MCA or CCA method, or use some linear regression method to find out this relationship. And then with that, you will be able to find out the trip generated by each TAZ zone, and the trip attracted by each TAZ zone, and so on. So that will be the origin destination information. And after that, we will have the trip distribution. For the first demo, we have the trip distribution to identify how many trips will be assigned from one origin to one destination. And then after that, we're going to have the mode choice to determine the discrete choice model to determine what's the portion of the trips will use this mode, and how many of the trips will use this route, and so on. So this would be the this is the 4-step model. It does not involve with the real world traffic conditions. Instead, it comes from the socio-economic features of the network. But as the traffic engineer, sometimes we cannot conduct this kind of survey. This is a it's very expensive for us to conduct a survey. But with the modern detection technologies like the loop detectors, the connected vehicles, the cameras installed on the road, it will be relatively easier for us to observe what's the volumes of the traffic on the road for each link on the road. And then we will be able to think about whether it's possible for us to use this volumes, the traffic flow data to calibrate the OD matrix. And that's the purpose of the QueensOD. And this software can help us to quickly generate the OD matrix for the microscope traffic simulations. And also there will be multiple versions. They have the small version, medium version, large version, and a huge version, which will be applied to different scales of the road network. The one that I shared with you is the small version, which will be able for you to work on the network with maximum 250 links and 250 nodes. And for the macro zones, which would be the TAZ zones, the maximum number is 10. And they also have specified the origin destination pairs and so on. But you always have the chance to get achieve the software for the larger network. And before I go to the tutorial of the QueensOD software, I would like to introduce some fundamental knowledges to conduct this type of the OD matrix estimation. So first of all, this estimation also based on the maximum likelihood function for the OD matrix. It tries to maximize the possible ways to assign the trips for each origin and destination. If you recall the gravity model, we have the similar terms. We have the similar terms. We have similar terms here, as showing the highest maximum number of possible ways for us to assign the trips to each origin destination zone. But here, for the QueensOD, it adds an additional concept, which would be literacy IJ. It represents the seed trip between the zone I, the origin I, and destination J, which will be the one that we have already conducted in the previous survey or from the previous city information. It's not necessary to be true or not necessary to be accurate, but it can give us some preliminary knowledge about what's the tree OD matrix looks like. And with that, it will help us to reduce the complexity of the estimation. I guess here I have some. I get a typo here. Let me quickly modify this. Okay. And so that's one objective we want to maximize. We would like to maximize the possible ways to for us to assign the trips for each origin and destination. And the second thing we need to think about is about the traffic volumes. We will be able to observe what's the volumes of the traffic that we can observe. We can collect it for each link. Say that for the link A, we know the for link A, we know the volume as VA prime, and assume then it should be the VA prime, the volume should be the same to the summation of Tij times Pija. Here Pija, the percentage of the trips from the origin I and the destination J traveling through the link A. So that's the that should be the ideal volumes that we're gonna observe on the link A. And then it comes to the second objective. We would like to minimize the difference between the estimated volume on the link A and the observed the volume on link A. So we will summarize this one for the whole network with no matter what with a lot of links, and use the square arrow to represent the square arrow of all the links to represent the total errors. And with that we will also want to minimize the sum of the square error between the observed and the estimated link volume. And that's the second objective. We would like to satisfy, we would like to find out the OD matrix, which would be the Tij, that's the estimated Tij, to satisfy the requirement of both objectives. And to do that, we're going to start with the second objective about the difference between the observed link and the and also the estimated observed volume and the estimated volume. And of course, we need to we can rely on the first order partial differential equations, and to if we conduct this process, you can find out in the constraint. So this constraint gives you the so this constraint gives you the information for the observed link and observed flow and estimated flow. And for the second constraint, for the second objective, which would be the maximization about the possible way for us to maximize the way for us to assign the trips to each origin destination pair. We will actually be able to apply this constraint that we derived from the second objective to the first one, and then we have the objective for both. We have the combined objective for both targets. One is minimizing the errors in the link flow. The other one is maximize the number of the ways to assign the trips. And similar to the gravity model, in order to conduct this kind of estimation maximization problem, we need to rely on the Stirling's approximation to convert the factorial functions to some linear functions, which can help us to simplify the calculation a lot. And once you conduct this kind of approximation, we can get the last equation in this page. And this equation can be further simplified by, if we go to check what's the components here, the summation of Ij for Tij will actually be just the total number of the trips. This is what we defined. So we can actually remove these two terms. We're going to remove these two terms from the equation, and with that we will have the final objective function, for the OD estimation. And in this equation, you know the rate of the trips, the volumes on each link, and they have a lot of other parameters you need to calibrate Tij. You also don't know the value of the total number of trips, capital T. And to solving this equation, this optimizing problem is very complicated. Of course, you don't want to do it by your hand. So we will rely on the software to conduct the estimation. So that's the basic information we need to know about the OD estimation with the link flow. We were actually trying to achieve the similar objectives to the gravity model, but we need to add the constraint from the observed link flow rate. And the one that I showed here was actually based on the error, the sum of the square error, but we can also rely on some other objectives. The first one is the least square error method, which is the one we just explained. This one is commonly applied. We want to find out, minimize the sum of the square errors between the observed and the estimated link flow rate. We also can use the second method, the least relative error method, which will show what's the sum of the square of the relative error, which the relative error is defined as VAO, that is observed flow, minus VAE, that is estimated flow, divided by VAO. And similarly, we can go to get the we can try to find out the what's the least Poisson error. So compared with the least relative error, we will replace the one at the bottom as the square root of the VAO. So this is the three different errors, and those will be three different methods applied in the QueensOD. And in the software, you have the options to decide which method you're going to use for the estimation. And of course, different methods will give different results. So let's go to check one example. Here you can see that there's a link. There's one OD pair from A to B. We have the observations about the flow on link 1 as 100 vehicle per hour, and on link 2 as 200 vehicle per hour. Then we want to use this information to estimate what's the demand from the origin A to destination B. This is quite tricky. Ideally, well, if you have, let's just remove this. Don't consider this number. If we have 100 observed from link 1 and 100 observed in link 2, then obviously for the demand from A to B, it will just be 100. This is straightforward. But now the issue is like these two numbers are not the same, so we need to rely on the method we proposed previously to quickly find out what's the best OD values, what's the best demand to minimize the errors. We define the square error, the relative error, or Poisson's error. So for the first method with the least square error, we're gonna try to find out what's the minimum value of the sum of the square errors from A to B for both links. And on link 1, the flow is 100. Link 2, the flow is 200. And if we go back to check the definition, that will be a summation of VAO minus VAE square. So here we have two links. So assuming that the demand from A to B is x. From A to B is x. Then we will have the summations of 100 minus x squared plus 200 minus x squared for link 2. If we want to minimize these two, this equation, with that you can find out the optimal value of x as 150 vehicle per hour. That's for the first method, and which means that the demand from A to B is 150. And for the second method, we will use the relative error. So with that, we will change the error term as 100 minus x divided by 100 square plus 200 minus x divided by 200 square. And if you solve this optimization problem, you're going to get the result as 133 vehicle per hour. And similarly, you can conduct the least Poisson error method by replacing the bottom with the square root of 100 and the square root of 200. And solving this minimization problem, you get the result as 144 vehicle per hour. So that's the one simple example about the how we're going to get the estimation of the demand from A to B. And now we will, in the second example, we're going to check in a more complicated case. We have the three links from A to the one in between. Say that this one's D. From A to D, the volume is set as 9,000. From D to B, the volume is 10,000, and from C to D is 100 vehicles per hour. Now we will need to check what's the result they can provide to us if we have the least square error method, the least relative error method, and the least Poisson error method. I have listed the solution here, but I would like you all have the well, probably some of you work on the least square error method to double check whether it's the same to this one. The some of them work on the least relative error method, and some of them work on the least Poisson error method to check whether these numbers are correct or not. So how about Ali and Xiaoyan, you work on the first one. The Haoyan and Yasmina, you work on the second method, and the rest work on the third method, the LPE method, to double check whether you can get the same results. I would like give you like 5 minutes to work on that, and I'll probably can get a longer. You don't need so long time to do it. Yeah, just give me a heads up to see whether you can get the same result. Okay, do you all get the result? So Ali and Xiaoying, have you double checked whether you get the same result to this one?
Yeah, I got the same exact result for the TAB. My answer is 9300 vehicle per hour, and exactly the same for T between C and B.
Yes. So in this kind of analysis, you need to assume there are two variables you need to estimate, which would be the demand from A to B and the demand from C to B. That's the TAP and TCB. So you set as x1, x2, and then apply the equations. And I see that Yasmina said that the also the least relative error method can have the same result. What about the last one? Have you for the least percent error method, have you all get the same result? Okay, this is just giving the ideas about how the method is applied. The this kind of three different methods applied for the calculation of the OD matrix. It's a simple method. Later on, once I should introduce more details about the format of the input and output files of the QueensOD software, we can go back to check these examples and see whether the software can give us exactly the same result. So that's for the OD second example, and the I'm just to go to the next one. For more complicated case, like in the actual network, actual real world network, it's different, very different from the first and second example. You will only from one origin to one destination, you only have one route. But in reality, usually from between 2 points, there are multiple routes. And we will also be able to observe what's the flow from on each link. And but we have no ideas about how the demand from A to B is split on each link. And with that, we need to deal with the multiple route problem. And this is another example. Say that we have four links. We know the volumes as link 1 is 600, link 2 is also 600, link 3 and 4 as 200. And for this perfect case, we can find that the volume from A to B as the demand from A to B as 800. This is something very clear, but the other situations that those numbers does not match with each other, and we have some uncertainties about the routes or the splits, then the situation will be more complicated. In general, there will be three scenarios to deal with this multiple routes issue. The first one is like we know the routes and we know the splits for the volumes, then it will be relatively simple. We can just apply the three different methods, the least square error method, least relative error method, and least percent error method to do the estimation of the OD matrix. It will be the same to the first two examples. In the second scenario, if we know the routes of the from A to B, which route they're going to use, or which multiple routes they're going to use, but we don't know the splits, like from A to B here, we don't know what the portions of the volume from A to B is going to the route with link 1 and 2. We don't know what's the split of the second route. This is route 1. and this is route 2. We know these two routes, but we don't know what the split is. So with that, we will need to apply the methods, still the same methods, the LSE, LRE, or LPE methods to conduct the estimation. But we need to assume that there's an additional parameter, which would be the split. The percentage of the vehicles go to route 1 and percentage go to route 2. Put this split as an additional parameter in the optimization problem and find out the optimal split and the optimal demand from A to B. So that's the second scenario. The third one, which would be the most challenging scenario, is we don't know the routes. We also don't know the splits. With that, we need to conduct a three-stage process. In the first stage, we need to identify all the possible or the feasible routes from A to B. So those are all the feasible routes. And then we need to follow the calculation in the second scenario, apply the define the splits of all these feasible routes as the parameters, additional parameters, and apply the three methods, LSE, LRE, or LPE methods to estimate the optimal splits, the optimal OD matrix, and then combine feedback them to find out what's the most possible routes, multiple routes to assign a trip from A to B. So with this kind of method, you will not only estimate the trip rate or the demand from A to B, the trip matrix, but also identify the potential routes for them to take. And you will also be able to extend this method for the mode choice. If you have multiple modes, then they will be similar to the case of the unknown routes or multiple routes situations. So that's some fundamental knowledges, and it's not required for you to do the calculation by your hand. I will go back to check all these examples, example 1, 2, and multiple route examples again with the QueensOD software. But before I go to that direction, I would like to take a 10 minutes break, and then we go to the tutorial about how to what's the input and what's the potential output. Do you have any questions so far? Okay, if you don't have any questions, and I will take a break, and I'm gonna resume the meeting at 4:20. Okay, and with that, I'm gonna turn off my camera and my mic. Okay, let's resume the discussion today. And from the second half of this lecture, I'm gonna introduce all the necessary input files for the QueensOD, as well as the one necessary output file for you to create some OD matrix. So in order to apply the QueensOD estimation, you first need to tell the software what's the network, how the network looks like, and they actually have some specific input files to describe the network. And the figure here shows one simple network. It's probably not quite easy for you to observe. Basically, the network is consists of multiple components, as what we introduced in the Emerson. The network can be identified based on the node and the links. The links represent where the node represent where we're gonna start a link, where you end the link, or where the vehicles will enter in the network or exit the network. So here you can see the examples about the one grid network, not exactly grid network, but it will have the straight lines to represent the link, and the and also they have the node numbers to show where the link, where the start point of the link, where the end point of the link. It's a little bit more complicated. So let me try to give you a simple example. Probably create a new folder, a new slice. Okay, let's go to check the one example that we showed previously for the 3-link example. So for the 3-link example, we have what happens. I'm gonna switch to my other computer so that I can draw something. Just a moment. Let me add another one. Can you see my screen now?
Yes.
Okay, that's good, and I hope it's still recording. Okay, so let's go to check the example. Like we have previously, we have the um, we have the example about the 3 links, all right? And this would be the link 1. Can't forgot about that. This is 2 and 3. So this would be the small network, and we define this one A, B, C. I say this one A, B, C, D. A, B, C, D are the nodes, and the connections 1, 2, 3 will be the links. So to represent the links, A to B, A to D will be the link 1, and C to D will be link 3, and D to B will be link 2. So that's the how the link is represented. And with that, we need to, in order for the system to understand what the link is, what's the node is, we have to specify the location of the node. So A, B, C, D, we have to give their coordinates. And for the links, we have to specify what's the start point of the link, what's the end point of the link. And of course, there are more features about the link. So so we start for the for the model input. For the model input, there will be the input file. The input file should have the format. I mean, for this QueensOD, for the model input, we need to have a set of the input files. In this input files, only the input file 1, 2, and 6 are required. The input file 1 is the node descriptor, which will show the information about the node. And 2 would be the link descriptor, which will show the information of the link. And the links the file 6 will be the observed flow rate information. It will tell us what's the flow rate you're going to observe on each link. And these 3 are the required files. And the others like the signal file, the COD file, incident file, the turning movement file, the path file, and the actual OD file, they are not required. They could be, you could type them, you could input them in the simulation, in the QueensOD. They will be utilized as the additional file to simplify your computation or to improve the accuracy of your OD estimation. But they are not necessary. Only the file 1, 2, and 6 are required. And I'm going to show you more details about what's the format of the of these files. And the next thing is about the to conduct the QueensOD. I will let me change it to the other, change it back to the computer. I will, from now on, I may need to switch the sharing port frequently to show you how to do the how to use the software. So first of all, I hope you all have already received the you have downloaded the file I shared with you, which would be the QueensOD SML, small, medium, and large. And in this folder, there are 6 different examples: 2 link examples, 3 link example, 4 link, 5 link, and 8 link examples, and a QNet example. And here, you will actually have this is the manual. It's not necessary. This is the QOD R2.1 is the manual for this software. And there's one executable file, the application file. That is the QueensOD executable file. And let's go to see the one specific. First, let me go check. Give you a quick demo about how the software is applied. In order to use this software, you need to go to the command window. First, type the CMD and search CMD to get the command window out, and then navigate to the folder where this application file is located. So in my case, I put them in the go to CD desktop and course 704 nodes and QOD and QOD small, medium, high, and now we have navigate to this folder. You can apply the dir to see what's the files included in this folder. We have all these files listed in the folder. You can see them in the command window. And then I'm gonna try to show you how we're gonna run one example. Say that we're gonna run the example in the QNet. So with that, you need to first type the application file. So that is QoDs, which would be the application file we defined here for the small network. And then you need to specify what kind of example you want to check. So in this case, we want to check the example under the QNet folder and the QNet, the first example, QNet A. So that is navigate to the folder and QNet A dot QOD. That will be the extension of the file. And then we have conducted all the, you see that it's running the software and try to conduct all the estimations, and all the output files has been stored in this output folder, and you will be able to see the one that is folder 11, which will show you the OD matrix. I'm gonna give you more explanation about that one later. So that's how we're gonna use the software, and then let's go to check more details about the input file. So first of all, we need to define the master control file. The master control file is the one for you to identify one specific to run one specific example, or to solve one specific problem that they are working on. So the here in the for the QNet, for the example I just show you, under the QNet there's one file, QNet A. That's the one that I just run. It's the one master control file, and this one, even though the extension is the QOD, you can actually open them with the notepad. So say that open them with the notepad. Or any other similar soft applications, it's fine. Or the WordPad or Word, they all be fine. I'm just using notepad, and you can see the information. You can see the information set for this example. The first line is the description of this file. It's the QOD master file. We have with the QNet. It's just the descriptions about this file, and then it follows by 3 lines. And there will be actually some meanings about these 3 lines, and the meanings will be shown in this page. So in the second line, the The first element shows the estimation method applied. It has 2 digits, x and y. X would be the first digit and y is the second digit. And for the first digit, for the second digit, if it's choose as 1, means that you're going to use the least square arrow method for the link flow. And if it's second, you use the least Poisson arrow for the link flow arrow. And this, if you choose 3, that will be the link relative arrow for the least relative arrow for the link flow arrows. And the first digit x indicates the what's the method you will be applied for the seed matrix. This is usually not applied. It's only applied when you have specified the seed OD matrix, like you have preliminary estimated seed matrix, OD matrix, or some older OD matrix for you to use as the prior information. Similarly, 1 is the least square arrow method, 2 is the least Poisson arrow method, and 3 is the least relative arrow method. And for this specific example, the first element we're going to take is 1, 1, 1, which means that we're going to use the least square arrow method for the seed matrix, and the least square arrow method for the link flow arrow. And the second cell here, which would be the second element, it represents the number of the iterations. So we will stop the iterations for, in this case, we set it as 1,000 times. We'll stop it after 1,000 times, or we're gonna stop it at the with another criterion, the what's the errors, what's the reductions in the flow error. So if the minimum reductions in the flow error is smaller than 0.01, then we can stop the criterion. So that will be the 2 combined stopping criteria. If the iteration goes beyond 1,000, then we're gonna stop. If the error, the reductions in the flow error is below than 0.01, then we're gonna stop. So that's the meanings of the 3 parameters in the second line. And in the third line, there will be another parameters we're gonna set. First, the first one is the number of the trees to estimate how many of the trees for the trips from one origin to the destination to multiple destinations. And the second one is the number of the steps to considering shifting the demand from the previous trees. Like from the previous trees, how many, if we do the iteration, how many of the trips like in this case, if you set it as 20, means that it was 20% of them will be shifted from the previous iteration to the from one tree we defined in previous iteration to the one in the current iteration. And the 3 will be the weight factor applied to adjust the link travel time. To build a new tree, this is usually set as 0.1. That's the default value. We will not recommend it to do any modification. And the first one is the there will be some only the first parameter is very important. In the first parameter can be the value between among 0, 1, and 2. 0 means that you're gonna ignore the link that you set the volume as 0. This is quite important because sometimes in the real world, in the field observation, for some links you cannot be, you don't have any sensors there, so you do not have any flow observed. And in this case, if you set the first parameter as 1 and you set the volume as 0 for that link without a sensor, then in the calculation we will not put that link as the constraint. If you choose if this parameters change to 1, means that you're gonna treat this link as the other links. So it's just like if the value is 0 means that the actual flow there is 0. It does not mean that you do not have the information. And if it's 2, it means that we will assume that the flow on that link as 1, so it has the minimum value. And the second parameter is the capacity constraint. If it's 0 means that we don't consider the capacity. If it's 1 means that we have to consider the capacity impact. And also we have the last one. The last one is the link flow consistency. We need to make sure that whether the link flow is consistent or not. Usually we will set the value as 0. And we also have some other starting from the line 5. There will be some it will specify the input and output information. Line 5 represents where the input file is stored, and the line 6 indicates that where the output file should be generated and stored. And from 7 to 9, it shows the input file, the node file, which would be the node information, and 8 would be the link file, which will show the link information, and 9 would be the signal information, and 10 would be the seed demand information, which would be the original demand information. And again, for this 9 and 10, they are optional file. It's not necessary for you to set a signal file or the QueensOD file. If you don't want to set it, you can just simply change the value to none. Then we will not call the information. And 11 is the incident information. Again, you don't need it. But this one, the QNet 6, which would be the line 12, that will be the observed link information. Is the required information. So you must have this information, this file in your master control file. And for the rest, 13, 14, and 15, those are not necessary. It's optional, so it's not necessary for you to include it. And all the rest from the 16 to 22, those would be the field for you to specify the output file. For the there's only one file I recommend you to set it. That will be the QueensOD11, which would be the line 17. It's the estimated OD matrix file. It shows that the demand set for each origin to each destination in the network. For the other OD files, for the other output files, if you don't want them, you can just set them as null. With that, then the file will not be created. So that's the master control file. You need to set up the fundamental parameters for the OD estimation, as well as the required input file and the necessary output file. So that's the master control file, and you have to save this master control file with the extension of the QueensOD. So that's what you're gonna observe for this in this folder. It's in the QueensOD file, and that's the master control file. And now the next thing we need to learn is about the input file. Here I'm just gonna introduce all the necessary files. This table shows the information for the input file. Let me also show you give you the example about the input file. This one is too large. Let me give you the 3 link example. if you still remember the one that I showed previously about the three link example, we can go to check the meanings of each field in the input file. The first line is a description of the file. So this say that's the QNet probably QNet node coordination file, and the in the second line it gives us the detailed information about the nodes. In the second line there are three parameters. The first parameter 4 here represents how many nodes you have to set for the network. In this case, there will be 4 nodes, and the second one shows the scales for the x and y. Second and third shows the scales for x and y coordinates, but it's not used for it's mainly for the QueensOD. And then start from the third line, it shows the information about each node. And I'm just going to show you what's the meanings of each field. So the first parameter is node ID, and the second one is the x coordinate, and the third one is the y coordinate, and the first one is the type of the node. And if it's set as 1, it means that it's the origin. It could be the origin, it could also be the destination. But if it's 2, it means that it's only the destination. And if it's 3, it's only the origin. And if it's 4, it means that it's not the origin or destination. It's just something in between. It's the some intermediate node. And the fifth column shows the macro zone cluster number. It only applies for the nodes with the value of the fourth column as 1, 2, or 3, but not as 4. If it's 4, it does not have any value. It should be set as 0. And the sixth column represents the information availability indicator as not used, and the last column is the description about the node, and again, it's not used for this software. So you only need to pay attention about these first 5 columns. The first one is the ID, second one is the x coordinate, third one is the y coordinate, and the fourth one is the type of the node, whether it's origin or destination, and the fifth one is the zone ID information. So that's the input file. And for this case, if you go to check more details about this information, about all this information, we can quickly draw the let me just we can quickly draw the find out the location of the these 4 nodes. So 1 is 1, 1, and 2 is 4, 1, 3 is 4 3 is also 4, 1, and the last one 11 is 2, 1. I guess there might be something wrong here. Let me double check this these numbers. There might be something wrong about this link file. I guess it's not the it's not set the right, does not set the right value. This one should be something about 2 or 0. See that 2. So basically for this case, we have the node 1 as 1 1 and node 2 as 2 1 and node 11 as 2 node 2 as 1 2 and node 11 is 2 1 and node 3 as 4 1. So this is a 4 1. Does not have the pen here, so it's not easy for me to write. Let me see whether I can add my pen for this to write these things. I'm gonna switch to my other computer so that I can draw what happens there. Okay. So let me share my screen. So now we have, I hope you can see it. Okay. So we have the node 1 as the coordinate of 1 1 and say that this is at this point, and node 2 as the coordinate of 1 2 and node 11 as coordinate of 2 1 and node 3 as the coordinate of 4 1. So those would be the 3 nodes that we defined, and only 1 1 2 and 3 will be the zone the macro zone where the vehicle can be generated and can to enter the network or can exit the network. And now the next thing is the is about the link file. The link file is relatively straightforward. It's each link will represent what's the connections between two nodes. So the similarly the if we go to check the link file, the first line would be the so let me go back to this one. So we're gonna have several links. For the 3 link example, we will have several links. This is link 1. This is a This is link 2, and this is link 3. So I'm going to explain how we're going to represent these 3 links in the text file. So again, I'm going to need to switch back to my other computer. Okay. So for the link file, still the first line. The first line is it's a description of the file, and start from the second line. It shows how many links you want to set for the network. Well, in this case, we have 3 links, and there are some other parameters. They are not used by QueensOD. It's actually applied for another software. And then start from this third line. It shows the information about each link. Let me show you more details about the what's the meanings of each one. In this line, in the third line, and the other following lines, the first column represents the ID of the link. So link 1 connect from the node 1 to node 11. So the second column is the start node, the ID of the start nodes, and the third column is the ID of the end nodes. And this one, the first column shows the length of the node. It's the length in kilometers, and the fifth column shows the free flow speed on the link, which would be the speed limit of the link, and that's in kilometer per hour. And the sixth column shows the capacity or the saturation flow rate. That's the capacity of the link. And the seventh column shows the number of the lanes on the link. So how many lanes on that link? They say that here we set as 6. And then for the rest, all the rest field is applied for the other simulation softwares. It's not actually used in QueensOD. Only for the 11 and only for the 11 and 16, those are used. The 11 and 16 are applied when you have to set up the signal timing plan, or you have some specific splits you want to set for the simulation for the QueensOD experiment. Otherwise, you don't need to set them. In the examples that I'm going to show you, you don't need to set up those parameters. You can just apply those default parameters to run the software. So we will only focus on the this set of the parameters, column 1 through the column 7. So you will have the definitions about all those all those parameters in the for the network. So with that, you will have the network. You will know the geometry of the network. You will know the features of the links. And the next thing you need to do is just specify the what's the flow you want to assign for each link. And here I also in the slides I also show you some information about signal timing plan. if your network contains some signals, you can follow the instruction here to include the signal settings for all the crossings in the network. And here we have more details about how the signals are set, but it's not the required file for the QueensOD. And the other required file is the input file, is the observed link flow rate. And here I'm going to show you the example from the three link example. And here's the descriptions about the all the fields in this file. Similarly, the first line shows the descriptions of the file, and in the second line there are 4 variables. The first parameter represents the number of the time periods for which the link flow rate is observed. So the if you observe the link flow at every hour, and you observe it for 5 hours, then you will have 5 different time periods, and you need to specify this one as 5. And for this case, we only observed 1 period, so the value is set as 1. And the second one shows the duration. Of each time period. Say that for 1 hour, that will be 3,600 seconds. And you can also have the smaller durations if your data is collected at every 1 minute, then this interval is 60 seconds. And the third one shows the number of the links in the network, how many links you have observed you have set up to build a network. In this case, we have 3. And the last one, the first parameter shows the maximum link ID number. What's the ID number? What's the highest ID number for the link in the network? And that's the second line. And the third line shows some information in the in each period. So the first parameter shows the time defined as the end of the observation period. So for the first period, as the duration is 3,600, so the first period is from 1 second to 3,600 seconds. So 3,600 is set as the end of that period. And the second parameter shows the what's the period number. It's the first period, then set as 1. If it's the second period, set as 2. And then after that, you will have the information about the flow information for each link. So start from the first line, you can type the information, the flow information. So the first column shows the link number, which link you observe the flow. And the second column shows the observed flow rate. It's the hourly flow rate. What's the volume in vehicle per hour? And the third one is the capacity of the network of the link. So for this specific example, the capacity is set as 36,000. And the fourth one is the free flow travel time on the link. What's the travel time that when the road is empty, and how long the vehicle can drive from the start of the link to the end. And the fifth one is the travel time on the link when it's loaded with the observed traffic. If you have this information, you can type what's the travel time, what's the actual travel time of the link. And for the rest rest field is not used. It's actually only applied for the other more advanced functions. And then with that you can set up the parameters, set up all the parameters for the simulation for the OD estimation. And now I'm gonna give you another introduction about the output. What's the output you should expect? For the OD matrix, it's once you conduct the apply the software, the OD matrix is stored in the file 11. So that's the one that I showed previously in the master control file. You can also define your own name in that line. So in the file 11, let me also bring out the existing output so that I can see what's the meanings there. So in the file 11, basically you can go to check the what's the values there. The first line is the description, similar to all the other files. It's just a description of the file. And start from the second line, there will be some meaningful values. In the second line, the first one represents how many OD pairs you have estimated for the demand. So in the three link example, we only have two OD. We only have two OD show estimated from one is from the origin 1 to destination 3. The other one is from origin 2 to destination 3. Those information will also be displayed. And the second line, in the second line, the second parameter shows the number of the first OD pair loaded to be utilized by the model. If it's 0, then X is set as 1. So usually this is just the parameter set as 0, means that the whether we want to use all the OD whether we have all the OD information or not. And the third one shows the number of the last OD pair loading to be utilized by the model. And if we set as 0, means that all the OD matrix will be utilized, has been estimated. And the last one, 1.0, shows the global OD demand scale factor. So this is actually applied for your future microscopy simulations. If it's 1, means that the demand is loaded as the value you estimated. Like if it's 1, then the demand estimate from 1 to 3 is 9,000. Then we will load 9,000. If it's 2, means that we will load 9,000 times 2. That is 18,000 vehicles. So it's in a scale factor. So that's for the second line. And for the start from the third line, it will show the information about each OD pair. Basically, you just need to know what's the meanings of the first first 7 columns. So the first column shows the ID of the OD pair. What's the ID of this one for each OD? And the second one is the origin of the OD pair. And the third line is the destination of the OD pair. So this one, the first line, the third line here shows the demand from the origin I to destination 3, origin 1 to destination 3. And the first column shows the what's the actual demand for that origin and destination pair. And the fifth column shows the friction factor for the randomness, and this one is usually applied for the generation of the random to load the traffic randomly to the network. It's not applied for the it's not utilized for the QueensOD estimation, but it's very important for the microscopic simulations. And the next two shows the start time of the of this demand and end time of the demand. So in this case, we will only estimate the demand for the first period in 3,600 seconds. So we start from 0 and end at 3,600. And the rest will be generated automatically, so you don't need to worry about that. So just pay attention to those first 7 parameters. And with that, you know all the input, all the necessary input and output information for the QueensOD. And I'm gonna give you show you one example about how the QueensOD is conducted for the three link example. And let's go to check the details about the about this one, the first example. And here we will set the parameter as 1, means that we're going to use the least square error method to conduct the estimation. And now let's go to check the type of the information, the QoD S to 3 link, and the master control file 3 link A .QoD, and we apply the least square error method to conduct the estimation, and you get the result as, so what you get as result as it's a 90 from the demand. The demand from 1 to 3 is a 900 and 9,299, and the value as from 2 to 3 is 401. And this is the example that of what we show here. It's very similar to what you get theoretically. It's a 9300 from A to B, and so A is node 1, C is node 2, and B is node 3. So from 2 to 3 it's 400. This is quite similar, and that's based on the least square error method. And we can also try to check the second method. Say that if we go to check the second method, this is the 1, 2, means that we're going to use the least Poisson error. So let's go to check this one. And let's see what's the result we can obtain. So what we get at the for the from 1 to 3 is 9,415.9. From 2 to 3 it's 144. And the theoretical result tells us that from the least Poisson error method, the result is 9415 from 1 to 3 and 145 from 2 to 3. It's very similar to the one that we get here. It's very similar to the theoretical results. And now we can also double check the least relative error method, which would be the third example that I set in the so the 3 link C shows the one with the least relative error method. So you set this one as 1, 3, so which means I use the relative error method. And similarly, let's go to check the result QoD, and let's compare the results you from the software and what you have already calculated. From the software, get the result as 9,423, and from 2 to 3 as 104. What we calculate is very similar to the one from the software. So it's a 9421 and 105. It's very similar to that one. So that's what we can observe from the software. And for now, I would like you to do some practice by yourself and try to see whether you can get the whether you can use the software. And I'm here to help you to get familiar about all the settings. I would like for you to run the example in a 5-link example. Yes, a 5-link example. One to which was showing this figure. A 5-link example. The example has been showing all the files have been set in this folder, file link folder. We have already set up the node file. You can double check the node file to see which one it is, A, B, C, D, and also the intermediate nodes. We also have the link file. We also have the link file to specify 5 different links for the network, and we have the flow information loaded as 40, 60, 120, 70, and 30. And node A is for the least square error method, node B is for the Poisson error method, and node 3 is for the relative error method. So I'll give you a chance to do the practice by yourself, and just let me know if you have any questions. With that, I will stop recording the video for the preparation of the quiz.